review. In this video, we're going to go over the various kinematic quantities that we use to describe motion, the kinematic equations to solve motion problems, and how to identify and solve free fall problems. The first couple of quantities we encounter are distance and displacement. What you need to know about distance is that it's a total distance traveled, so that means that the path matters. The SI unit is meters, and it is a scalar. It does not have a direction. Next is displacement, which is not the same as distance. Displacement is a change in position. We use delta x to represent displacement. The final position minus the initial position. So what this means is that the endpoints matter. We don't care about the whole path, just where you started and where you end up. The unit is the meters, and it is a vector, so it does have a direction. Let's do an example. I travel to school and then go back home. We see in this picture that home and school are 10 miles away. So what would be the distance traveled? Well, the whole path matters. So we're going back and forth. So we're traveling 20 miles. What about the displacement? Well, we started at home and we ended right back where we started. So there's actually no motion, no difference in position from the starting to the ending point. The displacement is actually 0. Next are speed and velocity. Average speed is defined as your distance divided by your time. The unit is meters per second. It is a scalar. So that means that it does depend on the path because it depends on distance. On the other hand, average velocity is defined as our displacement divided by the time. The unit is also meters per second, but this is a vector. It's going to have the same direction as the displacement. It's only going to depend on the endpoints. Let's look at an example. True or false? The average velocity for a trip can be greater than the average speed for the same trip. So this is actually false. Because if you think about it, let's say that you're going from here to here and you're taking this path, right? So that average speed is going to take into account that whole distance divided by the time, while the average velocity is only going to take that distance from the starting point to the ending point divided by the time. That's going to be shorter. So in general, the average velocity is going to be less than the average speed. The only time that they're the same is if your path traveled is in a straight line. If you travel in a straight line, then that means that your distance is equal to your displacement as far as the magnitude or the amount of distance traveled. Next is average acceleration. Acceleration is how quickly velocity changes. The key word is that velocity has to be changing to have acceleration. It's defined as the change in velocity per time. The unit for acceleration is meters per second squared. It is a vector. Let's look at an example. True or false? Acceleration is positive when an object speeds up. This is actually false. It doesn't have to be positive. It can be positive, but not always. So we have to know, well, how do we know when you're speeding up or slowing down? That's the next slide. When you're speeding up, it doesn't necessarily mean that you have a positive acceleration. It means that your acceleration has the same sign as your velocity. So your acceleration and your velocity could both be positive, or your acceleration and your velocity could both be negative. That would be speeding up. On the other hand, if you're slowing down, that means the acceleration has the opposite sign as your velocity. So one could be positive and the other one would be negative. That means you're slowing down. So look at which way V and A are going to determine if you're speeding up or slowing down. Don't just think that positive acceleration means that you have to be speeding up. Next up are the kinematic equations. We use these to solve problems involving motion. How do we know when to use these? Well, If you can identify 3 out of these 5 variables in the problem that you are given, you can identify 3 of these as given and you're looking for another one of these, that's going to be a really good indication that that problem will use the kinematic equations. We have 4 kinematic equations. Notice that each of these has a different set of variables that are represented in the equation. I went ahead and wrote down the variables in each equation, but you could just look at them to see, right? This one has VF, VO, A, and T. That's what I wrote down. The reason I wrote that down is that you can see that way you can see which variable is missing. This equation does not have delta x. That means use this equation if you don't care about delta x. Next up, the second equation has delta x, VO, A, and T, so that means it does not have VF, the final velocity. So use this if you don't care about VF. Next up, this one does not have acceleration. We don't use this as much because we usually have acceleration, but sometimes we do use it. And this last one does not have time. So when you're using the kinematic equations, you have to identify 3 out of these 5 variables and the one that you're looking for, and that will tell you which equation to use. Notice that whenever you are defining velocity in these problems, you always have to specify, is it initial velocity or final velocity? Because these are 2 separate variables in these equations. Because these problems tend to be harder for students, let's go ahead and do a full example. A car traveling at 20 meters per second slows down to 5 meters per second in 3 seconds. What is its acceleration? The first step is to identify 3 out of 5 given variables. It's traveling at 20 meters per second. That's the initial velocity. So you go ahead and write that down with the variable. It slows down to 5 meters per second. That's the final velocity. VF is going to be 5 meters per second. It takes 3 seconds. That's the time, is 3 seconds. And what are we looking for? The acceleration. So A is going to be the unknown. If you write down all of these variables, then you can go through these equations and see which one is going to be relevant to solving this problem. The first equation here has these 4 variables that we just wrote down. So we're going to write this first equation, VF equals VO plus AT. Then I like to solve for the unknown variable before I plug in numbers. I'm going to get A by itself. A is going to be VF minus VO, subtract the VO to the other side, and divide by T. And then I like to plug in the numbers. So A is going to be equal to 5 minus 20 over 3. That's going to be negative 5 meters per second squared. Notice that the acceleration is negative, but we defined all of our velocities as positive. So our velocities were positive going to the right, our acceleration is negative going to the left. That makes sense because we are slowing down in this problem. The last topic is free fall. Free fall is a specific type of problems that use kinematic equations. If you can identify any of these 3 cases, then you know you have a free fall problem. If an object is dropped, thrown downward, or thrown upward, these are keywords that tell you, okay, we have a free fall problem, and now we can already write some of our givens down. And then we'll use the kinematic equations. If an object is dropped, that tells you that the initial velocity is 0. The thing about free fall, if one of these 3 things happens, the acceleration is always negative 9.8 meters per second squared for all 3 cases, so you can always write down that variable. If an object is thrown downwards, that just means if it's going down, that means it has a negative velocity. So we can say the initial velocity is less than 0. While if an object is thrown upwards, it's going up, then the initial velocity is greater than 0 meters per second. If an object is thrown upward, you could have the special case of symmetric motion, where the object goes up and down and comes back to the same height from which it was thrown. If you have symmetric motion, there's a couple other things that you need to know. the velocity at the top is always equal to 0. So if there's a max height, that's a very good keyword in a problem. Whenever you see max height, that tells you the velocity is equal to 0 at that point. The other thing is that the time to go up is equal to the time to go down. This can be helpful sometimes. And finally, the initial speed is equal to the final speed. Now the velocities are different because they're in opposite directions, but the speed, the actual value, the number, is the same for both. Let's do one final example for free fall problems. A package is dropped from a building takes 10 seconds to strike the ground. What's the initial height from which it was dropped? So this problem, we need to identify 3 out of the 5 given variables. It looks like we're only given one variable, 10 seconds, which is time. But we identify a key word, which is dropped. We said whenever something is dropped, that means the initial velocity is 0. And this also tells us it's a free fall problem, and that means the acceleration is negative 9.8 meters per second squared. So just like that, we have 3 givens, even though we were only given one number. Now we're looking for the initial height from which it was thrown, but if we draw a picture from which it was dropped, we know that it goes down, and the displacement delta y going down, if we can find that as our unknown variable, then that will give us an idea of the height from which it was dropped. So which equation has these 4 variables? If we look at them one at a time, it's going to be, oh, and I forgot to put v initial here for was 0. It's going to be the second equation, has all 4 variables. Delta y equals VOT plus 1/2 AT squared. Since the motion is vertical for free fall problems, that's why all the equations have y instead of x. Solve for the unknown variable. Delta y is already solved for. We can go ahead and plug in the values, do these 2 steps together. We can cross out the VOT actually, since VO is 0, and now we can plug in the values. Delta y equals 1/2 times negative 9.8 meters per second squared times, and sorry, our time was 10 seconds. A couple typos there. 10 squared. When we plug all of this in, we're going to get negative 490 meters. This makes sense because whenever something is going down, the displacement is negative. However, if we're just looking for the initial height, height is always a positive number, so we know that the initial height is just the absolute value of that displacement, 490 meters. That is all for this Chapter 2 review video.